Welcome back. Section 2, we're talking about monosaccharides. Monosaccharides are simple sugars, okay? And it's a Latin derivation, it just means sweet. But anyway, monosaccharides are simple sugars. They're not dimers or trimers or a polysaccharide, which might be cellulose, okay? And monosaccharides can be classified as aldoses, which contain an aldehyde at the terminal of the chain, okay? And ketoses, okay? These are the two categories. And ketoses contain a carbonyl at carbon 2 in the chain, okay? So aldehyde is carbon 1, it has to be at the end of the chain, and the ketone here usually is at carbon 2, okay? And so let me show you an example of this. Now, I can't speak for every professor on the planet, but for my class, I can tell you don't memorize glucose, fructose, mannose, all that kind of stuff, okay? Memorize aldoses and ketoses. So here's an aldehyde here at the top of the chain. So this is an example of an aldose, okay? And this is a ketone here, and this is at carbon 2, okay? It's always written from top to bottom, 1, 2, 3, 4, 5, like that. This is a ketone at carbon 2, or a carbonyl, and so this is a ketose, okay? A ketose, okay? All of the sugars end with ose, okay? Whether we're talking about glucose, which is a simple monosaccharide, or sucrose, which is a disaccharide, okay? So everything ends in ose. So aldoses contain an aldehyde and ketoses contain a ketone. Now let me talk about the naming, okay? All right, this scheme right here tells you basically how to name your aldose or ketose. And of course, the first step is to figure out, do you have an aldose or a ketose, okay? And let me write out this thing here. Okay, so how do you name a monosaccharide? You identify, does it have an aldehyde or does it have a ketone, okay? Then step 2 is to count the number of carbon atoms, okay? So if it's 3, it's tri, if it's 4, it's tetra, if it's 5, it's penta, hexa, hexa, okay? And then you leave the ending of the name as ose. So let's go back to glucose here, okay? And let's try to name this. So if we number the carbon atoms here, we can see that it contains 6 carbons. So 6 is a hex for 6 carbons. We said already that this is aldose, okay? An aldose sugar, okay? And it is a monosaccharide. So we would name this Aldo Hexose. Okay, so ALD is short for aldehyde, we just have an O in there, and then hex is short for 6, right? And all of your sugars end in ose. So how about fructose here on the right? We number the carbon atoms again. Okay, so this also has 6 carbons, so it's going to be hex in the name. It's a ketose, we said, okay? And so this would be a Keto Hexose. So let's write that out. Keto Hexose, okay? So ket or ketone is short, keto or ket is short for ketone, hex is short for 6, and it ends in ose, okay? So you're gonna have Aldo Hexose or Aldo Pentose or Aldo Triose, something like that, or Keto Triose or Keto Heptose or Keto Pentose, for example. So you're always gonna have the keto or aldo first, the number of carbons in the middle, and then the ose at the end, okay? So you just need to memorize the naming there, and that's what you do, okay? So you work down steps 1 through 3, and you assemble them in those 3 fragments of the word or the name of the saccharide, okay? Next thing I want to talk about is D or L sugars. Okay, And this comes back to the Fischer Projections, which you may or may not remember from previous courses on stereochemistry. So I'll review a little bit about that very briefly, or just refer you back to the textbook chapter on that. But if you have glyceraldehyde, for example, or any sugar for that matter, you look at the position of the bottom hydroxyl group, okay? So on the end of the chain, you have a hydroxyl group. You have a hydroxyl group here too, but that's not a stereogenic center. This is a stereogenic center, and you look at that last hydroxyl group on the stereochemical backbone, and if it's to the right, that's going to be a D sugar, okay? And remember, the capital D does not correspond to R or S. It corresponds to the direction that plane polarized light is rotated when this substance is stuck into a polarimeter. And this is actually also referred to as the plus isomer, okay? So D is plus, okay? It stands for dextrorotatory, okay? The glyceraldehyde molecule here that I'm drawing can also have the enantiomer where the OH is on the left. And this substance here, again, you refer to the position of the OH. It's to the left, and so this is going to be an L sugar. And this is also otherwise known as minus glyceraldehyde. So capital L stands for levorotatory. It means that the light is rotated in a counterclockwise direction or towards the minus, okay? So that's basically it. It doesn't really matter what substance you have. Let's take a look at some sugars. Now, it turns out that all of the D sugars are naturally occurring in the environment. So here we have a hydroxyl group on the right, and that's the lowest one with the stereochemistry. You know, there's a stereocenter there, stereocenter there, stereocenter there. So the one on the bottom of the chain, we look for that hydroxyl group attached to that bottom stereogenic center, and it's positioned to the right. So that's going to be a D sugar, okay? This one as well is a D sugar, and this one as well is a D sugar. Now, all of these molecules can eventually be broken down through a series of chemical reactions and very careful studies, all to lead to D-glyceraldehyde. And D-glyceraldehyde, remember, is one of the simplest sugars. It just has one stereochemical center there. And you have the hydroxyl group on the right, which means that it's going to be a D-glyceraldehyde, which you can infer, therefore, that the original sugar, ribose, glucose, fructose, is a D sugar as well, okay? So keep that in mind. If the OH is pointing to the left, it's going to be an L sugar, okay? So let's just randomly draw something here. All right, so how would we classify this? First of all, we've learned the three different ways of naming this. So this is an aldo, okay, because it's an aldose. It contains 6 carbons, so that's an aldokete, okay? And then we end the name with ose, okay? So this is an aldoketose. Now, is this a D sugar or an L sugar? We look at that bottom stereogenic center at carbon 5 here. It's positioned to the left, so that's going to be an L sugar, okay? So this is an example of an L aldoketose. All right, so that's the other thing about the naming. Just remember, if the OH is to the left, it's L. If the OH is to the right, that's the other way, capital D, okay? And so all the D sugars are naturally occurring there, okay? So that's very important to recognize and realize that, okay? So let's go ahead and do some practice problems here from the textbook just to make sure we understand this concept, okay? So problem 1 asks us to classify the following carbohydrates as an aldose or a ketose, and then insert the appropriate term to indicate the number of carbons present. For example, Aldo Pentose, Aldo Ketose, whatever, okay? So yeah, let's go ahead and do that. So, this one right here is an aldose, okay? And it has 1, 2, 3, 4, 5, 6 total carbons. So this is Aldo Hexose, okay? Aldo Hexose. And this one in particular is a D sugar. So let's just review that, even though the problem didn't ask us to identify that. Next up in part B, we have 1, 2, 3, 4, 5 carbons, and it's also an aldose, right? It's an aldehyde. So this is an Aldo Pentose. Aldo Pentose, okay? Pent means 5 carbons. And that hydroxyl group is orientated to the right, so that's also a D sugar. You might be wondering why all the ones on this page are D sugars. It's because they're naturally occurring, okay? So, or more prevalent in nature. So here we go, 1, 2, 3, 4, 5 carbons. This is a ketose because it's a ketone, and we would name this Keto Pentose, okay? And that's also in the D configuration, okay? Over here, 1, 2, 3, 4 carbons is tetra, right? Tetra. So this would be called, and it's an aldehyde as well. So this is going to be Aldo Tetrose. We don't say tetraose because the A and the O are 2 vowels together. So just like the naming conventions in general chemistry, we drop off the A, okay? And that's also a D configuration. This next one is a ketose, right? Because you have the ketone there, and this is 6 carbons. So this is going to be a Keto Hexose. Hex means 6. It ends in ose, as do all the sugars, and this is also in the D configuration, okay? Let's go ahead and do part 24.3. Problem 3 asks us to determine if it's a D or L sugar. Okay, so let's do that first, and then we're supposed to answer the second part of the question, okay? So, so right here, this is a D sugar. This is a L sugar because it's on the left. This is a D sugar. This is a D sugar. And this is a D sugar, okay? And then we're supposed to assign a configuration for each chirality center. After assigning the configuration for all of the chirality centers, do you notice any trend that would enable you to assign the configuration of a chirality center in a carbohydrate more quickly? Okay, so we're gonna do like A and B, we're gonna notice the pattern, and then we're just gonna very quickly do that for C, D, and E, okay? Is that a good plan? So what we wanna do here is look at part A. Now, when you look at part A here, what you want to realize is that the horizontal substituents are coming out towards us, and the vertical substituents are going back from us. I like to call this a bow tie configuration because it's kind of like a bow tie. You know, you have the wedges that are coming towards you, okay? The lightest substituent is always going to be coming towards us, okay? It's always going to be coming towards us. It doesn't matter if it's on this stereochemical center 3 or this one at carbon 2, okay? So yeah, so what we do is let's identify this stereogenic center, okay? This is a hydrogen that has the lightest substituent, and then we have a 3-way tie. We have a carbon, we have an oxygen. Oxygen is the winner here, right? Because oxygen has a higher atomic mass than carbon. The periodic table goes C, then O, then N, then O, right? So oxygen has a higher atomic number than carbon, so this is priority 1, okay? And then we have 2 carbons. There's one that's connected to the aldehyde and one that's connected to this just OH, okay? So remember that double bonds count as if that carbon is bonded to 2 oxygens, and this single bond to an oxygen, this single bond to this carbon is counted as just 1 bond to a carbon, and this single bond here is counted as 1 bond to oxygen. Okay, so 2 oxygens on the top, 1 oxygen on the bottom, so the 2 wins out. So that's going to be priority 2, and this is going to be priority 3. Okay, we rotate the car. It looks like 1, 2, 3 clockwise. Because hydrogen's coming out, we get the opposite result, so this should be counterclockwise, or S. Okay, so the stereochemistry at carbon 2 is S. Let's now look at the next stereogenic center, which is this carbon atom here, okay? And we need to do priorities, okay? So first off, the easy things to do is to label the hydrogen as the lightest substituent, the oxygen labeled as the heaviest substituent. And then we go out, okay? We have this carbon and this carbon. We'll call this A and we'll call this B down here, okay? And we'll kind of take a running comparison of what's happening. So at A, we have a carbon, and at B, we have a carbon, okay? Now let's look at A. We'll use, green here to analyze. A is connected to an oxygen, it's connected to a carbon, and it's connected to a hydrogen. And we write these elements from highest to lowest. That's how we always have been using the Ingold-Prelog rules to assign stereochemistry. So we align it, so the second runoff is O, then C, then H, okay? For carbon B, we have oxygen, okay? We have carbon, and we have hydrogen, all right? So we need to write down what that is bonded to, O, C, and H, okay? So that's a perfect tie as well. So we go out an additional carbon from that, okay? Here we are going on path A, right? So now we're going to look at this carbon up here that I'm highlighting in blue, okay? That's connected to an oxygen by this single bond, an oxygen twice because it's a double bond, and then an H. So that's O, O, H. And then down on the bottom, we have this carbon here that I'm highlighting, okay? That's bonded to an oxygen, a carbon, and a hydrogen, okay? So the first comparison is tied, and then you have oxygen here, which beats out carbon. So A wins the competition. A is the top chain that goes up towards the top, so that's gonna be priority 2 now, not 1, because oxygen, remember, is priority 1. So this is gonna be priority 2, and this is going to be priority 3, okay? This whole group is priority 2, this whole group is priority 3. So we drive the car, 1, 2, 3, it looks like it's clockwise. The hydrogen's coming towards us, so we get the opposite result, which is counterclockwise, which means it's S, okay? So at carbon 3, it's S. All right, so let me erase the scribbles here. Okay, now we're going to do the same thing for carbon 4. So this is 1, 2, 3. Carbon 4 is right here, okay? Right here. And remember again that we have these wedges here, okay? So here's a wedge, here's a wedge. And we want to identify the lightest substituent, which is this hydrogen. We want to identify the highest substituent, which is an oxygen, which wins out over carbon, all right? So once again, we'll call the top chain A and the bottom chain B, and we'll go out one by one to analyze and see what's going on, okay? So first, we compare these two atoms. So chain A and chain B, we have a carbon and a carbon. Okay, so it's tied. Now I'll use green like I did before, and we'll look at chain A. So we'll look at what's attached to this carbon. This is bonded to an OH, a carbon, and a hydrogen. And we list those elements from highest atomic number to lowest atomic number. B is right here. We look to see what's attached to that. So this is oxygen, carbon, hydrogen. So that's a perfect tie. There's no direct obvious winner yet. Then we go to the next carbon out, which is going to be those ones that I've highlighted. So let's look at chain A first. We've got oxygen, carbon, hydrogen. Okay, and we look at chain B, way down here. Okay, that's bonded to oxygen, hydrogen, and hydrogen twice. Okay, so that's oxygen, hydrogen, hydrogen. So the oxygen is good, but then, you know, the carbon wins out, okay? So that means that chain A, right? Chain A is the higher priority. That's the winner. Chain A is up on top. So that means this whole group right here is going to be priority 2. And this whole group, the B chain, is going to be priority 3. Okay? If we drive the car, it's 1, 2, 3. It looks counterclockwise. But since the hydrogen's coming out, we get the opposite result, which means it's R. So that's going to be 4R. Okay? I'm getting kind of tired of doing this, so I'm just going to skip to the chase here and tell you what the pattern is. Okay? Obviously, you're supposed to do this many times and get a feel for it and get skilled and really, you know, ingrain that in your mind so you really learn. But here we're pressed for time, so I'm just going to tell you the result here. What you'll notice is that carbon 2 is an S and the OH is on the left. Okay? At carbon 3, it's an S configuration and the OH is to the left as well. Okay? And at carbon 4, the OH is on the, it's an R configuration and its OH is on the right, okay? So what we can say is that since this is on the right, this also would be the R configuration, okay? So if we go back to our problem here, we can just, let me scribble erase the answers that I've already gotten for this, okay, to clean up this, this slide here a little bit, okay? And we'll go ahead and just label RS. So remember, S is on the left, R is on the right, okay? So this is S, this is S, this would be R, this would be R, okay? This OH is on the right, so it should be R, S, S, and so on, okay? Got this one here. Now, the carbons that I'm pointing arrows to are not chiral. They're not stereogenic centers because you need 4 different groups for there to be a stereogenic center, which means you need to have the cross, okay? So that in a nutshell is how you figure out really quickly with sugars if you have R or S. If it's on the left, it's S. If it's on the right, it's R. That makes sense, right? If it's on the right, it's R. If it's on the left, it's S. Now, don't get that confused with the stereogenic center of D and L sugars, okay? D is that very last and only last hydroxyl group. If it's on the right, we call it a D sugar. If it's on the left, we call it a capital L sugar, okay? So don't confuse D and L with RS. This is D and L correspond to an experimentally measured direction of rotation of the plane polarized light. R or S is just a theoretical assignment that we can do by looking at a molecular model. I want to end this here and thank you for watching, and we'll go ahead and jump into section 4 next.